In the forensic chemistry setting, identifying unknown substances can be a matter of life and death, explosive, non explosive. However, in the home setting, there are similarly high stakes. Is it sweet or salty? Is it edible or not? Is it good for you or could this really do significant harm if it is ingested? And in this video, I want to demonstrate how we can use a portable near-infrared spectrophotometer for this chemical analysis. During the Thanksgiving season, my mom was here, and then a few weeks later, my wife's mom was here, and they amassed a large variety of different cooking substances. Many of them were white or beige. And then just in our home, we have other white powders that we might use for cleaning, like an oxygen-based powder cleanser or white body powder. And so what I want to do is determine with a portable infrared spectrophotometer, can I actually begin to determine the utility of various white powders based on what they're clustering near? So would my sugars cluster together? Would my cornstarch and body powder cluster together? In addition to other patterns that might be revealed to us and perhaps hopefully surprise us. And so here you can see in this picture, I have a lot of the white powders that I'm showing here. And in order to test them, I just put a tablespoon or two into a white tray, and then I will sample that or test that using the near-infrared spectrophotometer. Here, it's a little bit easier to see what I'm performing the analysis on, and I've labeled each well in the tray, A through J, and then I will test around each of these. I was able to keep track of these powders using this powder metadata table, where tray 1, well A, is a sugar. And then I've also included a description of what it is so I could use these keywords to perhaps help me understand these clusters. If we go on to the next row, we have cornstarch and then flour, baking soda, sea salt. You can begin to see how, based on the sample name and the description, we might be able to determine the likelihood of the performance of that powder. So let's get to the analysis. Here is all of the data illustrated in the raw format. Let me show you what this looks like in the formal preview. And with this, you can see we have our spectrum ID. This is just my food products analysis campaign from the NIR device. And then here you see we have a lot of data. And in this format, there's not much context to this data. We have our wavelengths across the columns, and then in each row, we have the absorbance value at that particular wavelength. But this is where tools like Python come in handy because we can now look for the patterns within this data set. We can clean up the data if necessary and start trying to extract insights that can help us understand more about the white powders in this study. So here we begin the analysis of exploring the white powders using Python and in our VS Code environment. To begin, as always, I will set up the environment. I'm using a special notebook that I'm going to use to help drop the columns. That's called this dropcol.py. And here is just a list of columns that I oftentimes drop when I'm analyzing data from this device. And it helps to make the notebook a little bit cleaner. So like other modules, you can import this module and then I can use what I'm calling the column variable as a way to, as a shorthand to help me clean up the rest of this data. And so here is a preview of that metadata table that I've already shown you. And then in the next cell below, I will read in the data as a CSV and then use this call.calls to drop the columns pretty neatly. This calls to drop refers to this list here in the file. And again, it just makes it easier without having to overload this code with common steps. So this is a nice trick for you to use if you want to clean up your code and you have some steps that are oftentimes repeated, even if they're not functions. In the next line, line 2 here, I'm going to set the index to spectrum ID and then essentially just select my wavelength data using this .loc method and starting at wavelength 1454. And then of course, we're going to clean up our data using apply SNV. This is the standard normal variant, and it really helps to correct for scatter in the data, which is a common phenomenon in these spectroscopic techniques. And then I want to create another data frame called class DF, which is just the extraction of the measurement description of that data. So let's run these cells and I will show you what they look like. Let's run this cell and insert a new cell at the bottom. And here's where we begin with our data frame. we have our measurement description column, and then we have our wavelengths here. And so in this first line, I'm just setting the index to spectrum ID here, and then selecting just the analytical data, this 1454 and beyond. In the class DF, I'm doing the same initial step, which is setting spectrum ID as the index, but then I'm just selecting the measurement description. And so I'm creating two data frames, one with the analytical data and one with the class data. This is just going to help me assemble the data frame later after we do PCA on the overall data set. In line 5, I am taking my metadata and I'm just setting all the string variables to lower. So if we look here, I am setting all of the sample names to lowercase. If you look at the original data, you see that the case varies. We have title case in many cases, but here for the MSG, we don't use the title case. And so by setting the case and locking this to lower, it'll just make it easier and more consistent if we want to select based off of that case. This, again, is another way to help avoid a headache later on in your code, particularly if you're receiving data and that data was not labeled with consistent type or cases. So in the next cell, we're going to do a lot of work. So essentially what we're going to do is first perform PCA, and then upon plotting that PCA data, we're going to color each point by class DF. And so to begin, we're going to perform the scaling on this analytical data using the standard scaler from scikit-learn. And then we're going to chain a couple steps together. We're going to establish our PCA method here, where we're going to use 4 components, and then we're going to fit and transform our scaled DF, our scaled data frame we created in line 2. And then we're also going to create a data frame at the same time. And so normally I write all these steps out explicitly, but I want to show you how we really can combine a lot of these steps if we're doing the same process over and over again. And since I know I want 4 columns and I'm creating a data frame, I'm going to call those columns PC1, PC2, PC3, PC4. And then I'm going to create a new column in my PCADF called class, which would be the class df.values. So let me show you what that variable looks like. It is just this array here, where you can see we're just extracting out the values, which is really important because if we don't, and we just try to create it without calling the values attribute, we have this series here, and it actually won't work in this manner. We can't create this new column from the series. We have to do it from the array. So next, I want to begin setting up my plot, my scatter plot. I'm going to set X and Y to PC1 and PC2. Again, I want to show you a more sophisticated way where we can do all of this in a single line to define those plot parameters. And then I'm also going to initially color the plot by the class column we just created. And many times when I'm plotting data in my real world setting, I use the X_Y_ so that I can then pass those into the variables into my scatter plot or whatever type of plot I'm trying to make. And then I'm just selecting some of the attributes I want to improve what the plot looks like. And here we're also going to pass in our PCADF as our data and then apply a few more changes to the plot to improve the way it looks. Now, when it comes to annotating our scatter plot, it still is kind of annoying, to be completely honest. So without these 2 lines here, let me show you what this plot looks like. We have this here where we can begin to see we have some extreme points out on the left top and bottom. We have a group in the middle, but because we have so many, it's really difficult to associate these colors with these respective plots, particularly for the green samples, one of which is an oxygen-based powder cleanser. The other is a sugar. Now, we could possibly guess that this green is likely the sugar because we see that it's next to purple, which is the powder sugar. However, to be more sure, it's always best to just then directly annotate this plot, or we could look for new ways to add information to the plot itself. Now, in order to annotate, we have to do this using a for loop, and I oftentimes also use enumerate to help me navigate the logic for this here. To do that, we're going to loop through the various rows of the class metadf sample name column, and then we're going to use the plt.annotate function to annotate our data. So this here is the location of those points, which will be based on the PCADF. And then we're going to use the text argument, which would be the sample name using a font size of 20. Actually, let me make this a little bit smaller. Let's do a font size of 18. When we do this, we now add those points to this plot. Now it looks a little wonky because I have all of my replicates here. So in this case, we have our MSG, and because I have 3 replicates, or I've done this in triplicate analysis, the text is a little sort of kind of makes your eyes cross-eyed a little bit. So typically what I would want to do is just average these points together. But for you to see this step, I wanted you to see that we could do this on the original data. We have the same thing here for sea salt. You can see that the salt itself is actually really different from all the other points in our data set, as well as a powder laxative, which uses a polymer-based laxative to help loosen your stool. And then interestingly, we have our oxygen-based cleaner and our cooking baking soda. If you can see, maybe not surprisingly, that these are close together. And then in the middle, we have an interesting group here that is pounded yam, baking powder, semolina, and body powder. So again, that's actually a really interesting group, and there might be cornstarch in there. This blue is the cornstarch. And so I do want to begin to see, well, why does this group come together? We can see that this group are the sweeteners. This group makes sense here because baking soda and these oxygen-based powder cleansers are essentially the same thing as the base ingredient, but then the powder cleansers have extra boosters to help give extra cleaning benefit without bleaching. And so let's see if we can understand this here based on the metadata we have about this group. So if you go back to our powder metadata, we can see that if you look at the semolina, the pounded yam, the flour, they all share, let me see, they're all thickeners, it looks like. So we see that the flour is a thickener. We see the cornstarch is a thickener. We see that semolina also is a thickener. So let me show you how we can take advantage of this insight based on the metadata provided. We can, instead of coloring by class, we can color by the class description. And in that case, I want to show you that we can actually just select for specific keywords and create a list that will help us with the illustration. And so what I'm showing here is that we're going to select the class meta description, and then I want to chain in some additional logic where I want to just see if this string here contains the substring thickening. And when we set case equal to false, we don't want it to look for this specific case. So even if we have this here, we want it to still come back as true and false if it has this here. If we don't do that, this will become false for everything because we know that we are using title casing here. We do expect there to be a capital T. But just to be safe, let's just set this to false and the capital T. So here, let's change this here. We're going to comment this line out and we're going to just run this cell again as is. And we can see that the true is true where the substring thickening is present. And we can see that for powdered yam, semolina, body powder, these are all thickeners. Now, the body powder is interesting because it likely contains cornstarch. Or, sorry, the body powder looks like it's coming back as false, but it's near the other thickeners. And that's likely because it contains some cornstarch to help prevent the sticking of the skin meats. Because these body powders usually contain a lot of cornstarch to avoid chafing in the intimate areas. Additionally, baking powder probably also has some cornstarch in it to prevent clumps while it's being while waiting for use. And so this actually makes a lot of sense with how these different white powders will come together. Of course, if we were to look for sweeteners, these two would likely cluster. And again, the sea salt is very distinct from the rest of the materials in this particular study. So it would really be cool to extend this to beyond just white powders. But what if we look in 3 dimensions? Now, with Seaborn, you can do that, but it's not as inherently interactive. And so what I wanted to do next was to use Plotly Express, which has a really nice method called scatter 3D. And so instead of just passing in PC1 versus PC2, we could just add a Z dimension and have that be PC3. Of course, annotating a Plotly Express plot is significantly easier than a Seaborn plot because it already has a parameter that we can use called text, and then we just pass in the data we want to use for the annotations. And then we have a few updates to make the figure look a tad bit better, and then we'll render that figure using fig.show. Now, when we run that, again, we can see a couple of different things. We can see really how distinct the sea salt is even more, because even in the 3rd dimension, it breaks out quite a bit. Of course, in the other corner, we have our powder laxative, which I guess is pretty good that it's away from most of the other foods in this study or powders in this study. We also see that our baking soda and oxygenated cleanser is pretty close to each other. And the accent MSG kind of stands off a little bit too. So it'd really be cool to explore more powdered cooking ingredients to see if there's anything that kind of moves towards that MSG or monosodium glutamate area. The sugars are close to each other. The other thickeners in this middle are also really clustered very nicely, with baking powder kind of sitting between the baking soda area and these thickeners, likely due to the addition of that cornstarch, but to a lesser extent. And so even with this study, you can see we're getting a lot of insight into these various foodstuffs and other cleaning products, and the insights that come from the composition that we can understand through the lens or through the light of a near-infrared spectrophotometer. Now, when we combine these skills with Python and some context of the ingredients from the meta descriptions, we can do a lot more with this. And what I'm hoping to do in the future is to extend this to not just our white and beige powders, but what if we extend this to an entire cabinet of ingredients, or go to an international market and figure out how similar these various ingredients are if we were to subject them to the same analysis. Now, the cool thing is a lot of this can be done through plastic, and there have been studies that have actually analyzed various meats through plastic. So we may not even have to open them for this study, but we can attempt to test them through the packaging to avoid any contamination from our probe to these foods and to maintain their edibility. This can be great for quality control. This can be great for ensuring label accuracy. This can be great for a lot of applications in the store, in your home, in the factory. And if you want to see more of how we can leverage this and our data science skills for storytelling, like, comment, subscribe. And if there's any other foods you want me to look at, leave that below as well. And I'll see you in the next video. Peace.